Welcome to the next installment of our Balancing Chemical Reactions series of mini lectures. In this video, we're going to talk about how to balance a chemical reaction equation using the so-called algebraic method. So we're going to start off with a given chemical reaction equation. In this case, we're looking at essentially the process of photosynthesis, where we take water and CO2, combine them to form a complex carbon-containing molecule, in this case glucose, and oxygen. All right? So immediately when you see a chemical reaction equation like this, I hope that you've noticed that we have a rather significant imbalance in the number of atom types on each side. All right? Over here on the right-hand side in our glucose molecule, we have 6 carbon atoms and only 1 carbon atom over here. So just as with our general goal in balancing a chemical reaction equation, we want to figure out what coefficients we need to place in front of each one of these reactants and product species in order to obtain the same number of each atom type on the left-hand side and the right-hand side. Now, with the algebraic method, what we're going to do is essentially frame this problem as solving a system of algebraic equations. So the problem really comes down to determining these set of coefficients, all right, once again, that allows us to set up the same number of atom types on the left and right-hand side. So we have 4 unknown values here. We'll represent them by A, B, C, and D. These are variables. In order to solve for this set of 4 variables, what we need is a system of 4 equations. It turns out each one of these different atom types that are present in the chemical reaction will give us a single algebraic equation. So let's see how we can build these. We're going to start off by just writing out each one of the atom types that we have present in our chemical reaction equation: carbon, oxygen, and hydrogen. Now, for each one of these atom types, we need to construct a relationship between these stoichiometric coefficients, these unknown variables. So to do that, we're going to walk through and we're going to see that for each one of these carbon atoms, right, for each one of these CO2 molecules here, we have a single carbon atom. And if we have A CO2 molecules, this term here is going to give a total contribution of A times 1, right? Because there's only 1 carbon atom per CO2 molecule. There are 0 carbon atoms in this water molecule here, so we don't have any contributions from that. So we know that A times 1 must be equal to the number of carbon atoms on the right-hand side of the equation. On the right-hand side, we have this glucose molecule, right? So each glucose molecule has 6 carbon atoms. So if I have C glucose molecules, then I'm going to have C times 6, or C6 carbon atoms on the right. So this is our first our first algebraic equation that must be satisfied. Whatever coefficient is A, right, multiplied by 1 gives us the total number of carbon atoms on the left-hand side of the chemical reaction equation. Whatever coefficient C times 6 gives us the total number of carbon atoms on the right-hand side, and these two values must be equivalent. So we're going to go ahead and do the same thing now for the other 2 atom types. So our next atom type listed here is oxygen. We can see for every CO2 molecule we have, every 1 CO2 molecule we have, we're going to have 2 oxygen atoms. So we are going to have A times 2 oxygen atoms contributed from this first term. Now, our second reactant molecule, water in this case, also contains oxygen. So we need to include the contribution from oxygen atoms. In this case, every water molecule only has a single oxygen atom. So we are going to have a total of B times 1 oxygen atoms contributed from our waters. So now the total number of oxygen atoms from the left-hand side of the equation is our A times 2 plus B times 1. Now this must be equivalent to the number of water molecules on the right-hand side of the equation. So once again, we have our glucose molecule. The glucose molecule has 6 oxygen atoms. So if I have C glucose molecules, I'm going to have C times 6 oxygen atoms. Adding in the contribution from our O2s, we're going to have 2 times D oxygen molecules. So now adding both those terms together, we have the total number of oxygen atoms on the right-hand side, product side of our chemical reaction equation. And we've now completed our second algebraic equation that needs to be satisfied to find these coefficients. So we'll quickly move through our last one here. Hydrogen's only showing up in the first term here. So we're going to have 2 times B hydrogen atoms. And over here, we're going to have 12 times C hydrogen atom contributions from the glucose. And again, carbon dioxide and oxygen obviously don't have any hydrogen, so they're not going to contribute here. So what we've done here is we've used each one of the atom types to set up a separate algebraic equation that must be satisfied. Now, there's a problem. We have 4 variables, namely the 4 stoichiometric coefficients that we need to solve for, but at this point we only have 3 equations. So if we have 4 variables and 3 equations, we're basically up against the wall where we have an infinite number of solutions. In order to nail things down and get a definitive solution, we need a 4th equation. Now, this 4th equation can be chosen to be almost anything. And we can basically come through and set any one of these stoichiometric coefficients to actually any value that we want. And we can crank through and solve the system of equations. And then at the end of the day, we can make sure we have the smallest whole number coefficients. What I'm going to do here is use a little intuition to essentially make an intelligent choice as to what my 4th equation should be. If you look at our glucose molecule, all right, the glucose molecule has 6 carbons. This carbon dioxide only has 1. So right off the bat, you know the relationship between A and C, all right? We're given it right here. C has got to be, essentially if C was 1, A would have to be 6, okay? And by choosing that value, these terms match up nicely. So I'm going to go ahead and use that to guide that choice for this 4th constraint, or this 4th equation. So I'm going to go ahead and choose maybe either A equals 6 or C equals 1. It really doesn't matter. I'm going to go ahead and let A equal to 6, right, to give me my 4th equation. Now that I've set up all of my equations, our next task then is going to be to essentially solve these equations to find the values for the coefficients. And once we've done that, we will have balanced the chemical reaction equation. So the method we're going to use for solving the system of algebraic equations is a method of back substitution. We're going to use known quantities and essentially substitute them back into the preceding equations until we one by one solve for individual values of all the individual unknowns. So we already know A, right? We're assuming A here to be 6. So if A is 6, right, we can use our first equation. And we can go ahead and number these guys here to make it a little bit easier to follow what we're doing. Okay. So we can go ahead and use our equation 4 and plug our equation 4 into equation 1. What does that give us? Well, A is 6. So if I plug in a value of 6 for A, right, we get A is equal to C times 6. Well, what this 6 equals C times 6 implies that C is going to be equal to 1. I'm going to scoot that over a little bit so that we can see that better on the screen. So 6, right, we're plugging in 6 for A, is going to be equal to C times 6, right, which tells us that our value of C is going to be equal to 1. Okay. So now we've got a value for C and A. Now we can use this equation that we've now constructed, again following the method of substitution here, back substitution, and now take these 2 values, all right, and look at the remaining equation and see, well, what other variables can we solve for? Given C, we can actually plug directly into equation number 3 here. So we can use equation number 3 to solve for B. According to equation number 3, B is equal to 2 so 2 times B is equal to C times 12. So if I divide both sides by 2, I get a value, B must be equal to C times 6. Now C we already determined to be 1, so that means we have B equals C, I'm plugging in 1 for C, and we get a value of 6 here for B. So now we have determined the value of C, B, we've set the value of A by assumption, so we only have one remaining variable to solve for, D. So we're going to use our last algebraic equation here, number 2, to solve for D. Now this one's a little bit more complicated here. So I'm going to go ahead and take these values that I have over here. We've already solved for C, and we've got our value of B. So we'll record these. C, remember, is 1, and B here is going to be 6. Now finally, we're going to use our second equation and solve for our last variable. Okay, so we're going to use equation 2, solve for our last variable, which is D. So my first step, we'll break this down step by step. I'm going to isolate D. I'm going to solve equation 2 to get D by itself on one side. So doing this, we're going to end up with a D times 2. So we're going to have D times 2, and then I'm going to subtract off the 6C to the other side. So I'm going to have 2 times A. Get this eventually, keep my color scheme correct. And then we're going to add on B, right? It's just B times 1. And then remember, I'm subtracting off C times 6. Okay, so now my goal here is to solve for D. So my next step is going to be dividing through each and every one of these terms by 2. So dividing through by 2, we're going to get a value of D equals A plus 1/2 B minus C times 3, because I've got 6 divided by 2. Now, I can take this equation and plug in all the values that we previously solved for. We know that A is going to be 6. Okay, so I'm going to plug in a value of 6 here. B, we determined to have a value of 6 as well. And C, we determined had a value of 1, so we're just going to subtract off 3. So what we have here is 6 plus 1/2 of 6, which is 3, minus 3, gives us a value of 6. So you can summarize this right down here. So we found our fourth variable. Now, if we plug this back in, we can now write down what we've determined to be each one of these coefficients. So our first one, A, is going to be a 6, okay, using this equation. B, taking a value of 6 using this guy right here. C takes on a value of 1. And remember, we typically ignore, or there's an assumed 1, so we won't, in practice, write down that 1 explicitly, but just so we can see where the numbers are coming from, we'll include it now. And we have our chemical reaction equation, where now we've plugged in our coefficients, and we can go back through and do a quick sanity check to make sure that now we have the same number of each atom type on the left-hand side and right-hand side. And this is the way you go about solving this problem using the algebraic method.